Okay, so we're going to be looking at section 2 out of chapter 8, which is estimating a population proportion. So we're going to be able to calculate confidence interval for a population proportion, as well as determine sample size and a few other things regarding the population proportion. So the first thing we're going to look at is the conditions for constructing a confidence interval about a proportion. You have to check these conditions, and when you're working on your AP test, it will also expect you to check these conditions. Okay, so the first condition that we need to check is that whether this sample or the experiment was random. Okay, so that's our first condition. We need a data coming either from a random sample or a randomized experiment. Okay, we need to be able to draw conclusions that go beyond the data. Okay, and that this also allows us to introduce some chance into the data production process. Okay, and if we don't do that, then our intervals won't come out quite right. Okay, you also need to check your 10% conditions. Okay, remember, our 10% conditions allow us to use our formula for standard deviation of the proportion, right? It would allow us to use this formula here if we meet those 10% conditions. Okay, 10% conditions assumes that we're sampling with replacement. Okay, but as a general rule, we are not usually sampling with replacement. We are usually sampling without replacement, and it's usually from a finite population. So we need to be sure to check the 10% conditions so that we can know that we can be sure that we're able to use this formula here. Okay, we also then need to check large counts. Okay, we need, again, remember, you need both n times p and n times 1 minus p hat. We need both of those to be at least 10. Okay, remember what that tells us, right, is that we have an approximately normal distribution when we have both of those are greater than 10. And we need to have a normal distribution for constructing our confidence interval. Since we don't know p, remember before in the previous chapter it was np and then n times 1 minus p, not p hat. Since we don't know p, we can substitute p hat for p because remember in large random samples, p hat is going to be close to p. So we can substitute it in when we're doing our large counts. Basically with your large counts, you're looking at my number of successes with a proportion. Remember, both proportions we're looking for success versus failure versus the number of failures. So when you're looking at your sample, how many successes did you have? Is that greater than 10? How many failures did you have? Is that greater than 10? And you would satisfy your large counts. Okay, so let's look at this in action here. So we have this class, Mr. Vignolini's class, wants to construct a confidence interval for the true proportion, P, of red beads in the container. Recall that the class's sample had 107 red beads and 144 white beads. So basically what happened is the teacher put a bunch of beads into a container and that the kids couldn't see into. And the kids then had to take a random sample from that container. Okay, and now they're going to check the conditions for constructing a confidence interval and seeing if they meet those conditions. So the first thing that they need to do, right, is that they need to make sure it was random. And they did take a random sample out of the container. Okay, so they're okay with that. The second thing that they need to do is they need to check their 10% conditions. Right, and so in our 10% conditions, we are looking at, right, they had 251 beads in total, right? They had 107 plus 144, okay? That gives them 251 beads in total times 10, which means they had to have a population in the container of at least 2,510 beads. And the teacher told them that they had 3,000 beads. So they fit 10% conditions. They are less than or equal to 10% their sample size is. And then the last thing that we'll need to check is our large counts. Okay, and so for our large counts, we have how many successes versus how many failures, right? Our successes, okay, would be 251, that was our sample size, right, over our 107 out of 251, right, our failures versus successes. That gives us 107, which is greater than or equal to 10. And then our failures, right, n times 1 minus p, which again would give us our sample, 251 times 144, which is our failures, over 251, gives us 144, which is also greater than or equal to 10. So we satisfy our large counts for this. So their class could move forward with constructing a confidence interval for this particular situation, for this particular parameter. Okay, so let's look at the actual construction of the confidence interval for P. So the first thing we have here is we have our definition here of what we call standard error. So standard error is when the standard deviation of the statistic, there we go, maybe a little less blurry there. Standard error is when the standard deviation of the statistic is estimated from the data. So we don't actually have the true standard deviation, we're estimating it from our data. So instead of calling it a standard deviation, now we're calling it a standard error. Our formula for standard error is the same as long as we're meeting our 10% conditions. Our formula for standard error is going to be the same as standard deviation, right? Standard error of p hat is going to be equal to the square root of p hat times 1 minus p hat over n. Okay, since we don't know, remember that's the same as our standard deviation formula, except our standard deviation formula would have looked like that. But we don't know p. We're trying to find a confidence interval for p. So we don't know p, so we replace p with p hat if we meet our 10% conditions, and again we call it standard error. So it describes the same as it does for standard deviation. Standard error describes how close our sample proportion is. So it's not the same as standard deviation. It describes how close our sample proportion is going to be. So how close is p hat going to be to p? Okay, if I took repeated simple random samples of whatever size it is that you took. So that's what we're looking at when we calculate the standard error number is, which is how close our sample p is to the true proportion. Okay. And that's like I said, it's an estimated standard deviation. So to calculate this, we need to find a critical value. Okay, and we call this critical value Z with an asterisk next to it because it's not quite the same as a Z score. Okay, so we call it critical value Z, and there will be an asterisk next to it every time you will need to draw that. Okay, so we need to determine this critical value of Z to determine our confidence interval. Okay, so let's look at this standard curve that we have here. So we have standard normal curve. Remember, the mean for the standard normal curve is 0, and the standard deviation for it is 1. Okay, and so if we were looking for 95% confidence, okay, so we have this probability here is equal to 95%. So on each tail here, we have 2.5%, or an area of 0.025. So when I work backwards using my table A, and we can also do this on the calculator, we can determine that our critical value of Z is 1.96. Okay, that critical value of Z is going to be important when we calculate our confidence interval, because remember, to calculate a confidence interval, it's our statistic plus or minus the critical value times the standard deviation or standard error of the statistic. Okay, so let's look at an example of using this for a confidence interval of 80%. Okay, so our problem here is finding a critical value using table A or technology to find the critical value Z star for an 80% confidence interval. Assume that the large counts conditions are met, so you don't have to calculate your large counts condition. So let's look at what this would look like if we drew this out. Right? If I drew this out, I'd have my standard normal curve there. Right, 0. This time, though, my probability is 0.8. My area under the curve is 0.8. So what that leaves is 0.2 left over, right? If I have 100% minus 80, 1 minus 0.8 leaves 0.2 left over. So when I split that 0.2 between my two sides, I get a 0.1 on one end and a probability of an area of 0.1 on the other end. And so what I'm looking for is this critical value z here. So this is the point where I've got an area of 0.1 to the right under my standard normal curve. So I could use my table A. This is a little portion here of your table A. So you could use your table A and you could find where I have it the closest to 1, okay, the closest to 0.1, okay, and that would be my critical value. So basically my z-score here is a negative 1.28. So my critical value is a 1.28 here. Remember 1.2, and there's the hundredth place there. That's where I get the 1.28. Or I can put this in my calculator. Here's my concern. Okay, we've been having a little bit of trouble when we get super calculator dependent and we're not remembering what that stuff means. That was the conceptual stuff that we were having problems with on the multiple choice. Okay, again, you are welcome to use your calculator, but if you can't tell me what that means, then you are not going to be very successful on the multiple choice portion on the conceptual type questions. So if you're using your calculator, you're going to use the inverse norm function. Okay, and your area that you're looking for is not 0.2, it's just one of the tails. So your area is 0.1. Okay, my mean is 0 because this is a standard normal curve. So my mean is 0 and my standard deviation is 1. So my standard deviation is 1. And that will give me my negative 1.28. So which tells me my critical value of z asterisk is 1.28. So that would be 1.28 here and negative 1.28 to the left. So once we find that critical value, we can then start to actually construct the confidence interval. So remember, when all of our conditions are met, so we've checked our 10%, we've checked our successes and failures being greater than 10, our n times p, and our n times 1 minus p, we can then construct our confidence interval. And so remember, the formula, again, was our statistic. Okay, so here's my statistic, plus or minus my critical value. That's what we just calculated using either your calculator or your table A with the z-scores. Okay, times your standard error or your standard deviation. And so this, when we do this, this is called, and you're going to need to file away these names. This is a one sample z interval for a population proportion. You've got to file away these names. Okay, so again, it's a one sample z interval for a population proportion, right? It's a z interval, critical value of z there, right? So it's a z interval, and I only used one sample here. So I only have my p hat, right? So this is one sample z interval for a population proportion. Okay, so let's look at an example to calculate this. Okay, so we're back to the problem with the beads in the sample from class. So Mr. Vignolini's class took an SRS of beads from the container, got 107 red beads and 144 white beads. Remember, this is the same example we had before. So remember, our p hat for this is 0.426. Right, when we take 107 over 251, 107 plus 154 gives me my total, 144, I'm sorry. 107 plus 144 gives me n, right, which was 251. That gives me n. My successes here were 107, so 107 over 251 gives me 0.426, which is my p hat, right? That's my sample proportion. So in this example, you're asked to calculate and interpret a 90% confidence interval for P. Okay, so let's take this one step at a time. Let's do A, and then we'll look at B. Okay, so when I am, let me get rid of some of this. Okay, so when I'm going to calculate this, the first thing I'm going to need to do is I'm going to need to go ahead and state what I'm doing. Okay, so I'm looking for my 90% confidence interval for the true proportion of red beads that are in the container. Okay, if I want to find this, remember my formula for this is p hat, my statistic, right, p hat, plus or minus my critical value times my standard error, right? It's not a standard deviation because I'm estimating it. So it's not a standard deviation, it's a standard error over my sample size. Right, so I need to figure out what my critical value is. I know my p hat, I know my sample size, but I don't know what my critical value is. So again, I could, for this one, I want a 90% confidence interval, right? So I've got my probability is 0.9. That gives me 0.1 left over. So on each tail, I've got a probability of 0.05. So I have an area of 0.05. So I can either go into my table A and find where it's closest to 0.05, right, and pull it out of there and get my negative 1.64 for my z-score, which makes my critical value 1.64, or I could plug that into my calculator. If I plug it into my calculator, I've got inverse norm, okay, with an area this time of 0.05, okay, still though a mean of 0 because I'm using my standard curve, and a standard deviation of 1. And that also should give me negative 1.645. So that again translates into a critical value of 1.645. You'll notice it's not negative 1.645, it's 1.645. So when I plug all this into my equation, right, I'm going to get 0.426 plus or minus 1.645 times the square root of 0.426 times 1 minus 0.426 over 251. Okay, and when you calculate all of that out, what you end up with, so that's going to equal 0.426 plus or minus 0.051, which is equal to my interval, right? And so my interval is going to go down as low as 0.375, okay, comma, and then it's going to go up as high as 0.477. So my interpretation of this goes back to my statement from the previous section that we needed to remember, that we are 90% confident that the interval, in whatever our interval is, in this case 0.375 to 0.477, captures, and then we put it in context, the true proportion of red beads in Mr. Vignolini's container. So this is what your context should look like. We are 90% confident that the interval 0.375 to 0.477 captures the true proportion of red beads in Mr. Vignolini's container. Specific, about the container, about what you're looking for, specific to the problem. You have to do that. If you are not doing that, then you will not get full credit. So don't shortchange yourself when you do your practice problems. All right, so let's look at part B. So for part B, it wanted to know that Mr. Vignolini claims that exactly half the beads in the container are red. Use my results to comment on this claim. Use my results from part A to comment on this claim. So he claims that half the beads are red. So basically what he is claiming is that P is equal to 0.5. Well, based on what I got in part A, I would say that we have a good reason to doubt him, because that's not captured within my interval, right? The proportion, we have a good reason to doubt his claim and state what his claim is, right? We have a good reason to doubt his claim that half are red because 0.5 is not contained in the interval of plausible values. Okay? So we would doubt his claim and we would question that. So when you're doing these kinds of problems, you want to follow your four-step process. And your four-step process is based off of AP reading, AP rubrics. So you want to be sure that you're following this four-step process so that you can guarantee that you're going to get full credit when you are writing free response questions. So the first step would be the statement, right? State your parameters you want to estimate and at what confidence level. For instance, I wanted 90% confidence. Okay, and I wanted to find the true proportion of red beads in the last example that we did. Okay, the next step is to plan it out. Identify your appropriate inference method. For example, we only know one right now, which is a one sample Z interval. So that would be my appropriate inference method. I was using the one sample Z interval, okay, and I checked in checking conditions. 10% conditions, large counts. Okay, so make sure you're doing both of those, 10% and large counts. Then you're going to need to actually do the work if the conditions are met. Okay, either show all of your calculations, which you don't necessarily need to show a formula like copied from the formula chart, because if you get the notation wrong, if you write a p hat where you should write a p or a p instead of a p hat, you could end up not getting full credit. You can go ahead and substitute your numbers straight into the formula, and then you don't have to worry so much about the notation. And then your final step would be your conclusion. Interpret your interval in the context of the problem. Okay, so, and again, refer back to that statement. We are, however, whatever percent confidence that the true proportion is captured in whatever interval you found, a true proportion of whatever it is that you found, okay, in context, and then is found in whatever interval you calculated. Okay, so let's walk all the way through one example of this. Remember I told you if you're doing these problems right, half your problems are going to take up half a page, okay, or more. So we're going to go all the way through the 4 steps with this problem here. So the setup here is that the Gallup Youth Survey asked a random sample of 439 U.S. teens aged 13 to 17 whether they thought young people should wait to have sex until marriage. Of the sample, 246 said yes. Construct and interpret a 95% confidence interval for the proportion of all teens who would say yes if asked this question. So step 1, right, was our statement, right? We state. Okay, well, what we're stating here is that we want to find the true proportion of teens aged 13 to 17. So all the context that's in the problem, okay, whether young people should wait until marriage to have sex with 95% confidence. I need to state that. Okay, so this is my statement. We want to find the true proportion of teens aged 13 to 17 who believe young people should wait until marriage to have sex with 95% confidence. You can reword that a little bit, but those things all need to be there. The fact that it's teens and their certain age, what they're asking them about, and how much confidence you want there. Okay, so step 2 then would be our plan. So in step 2, we need to plan it out. So I need to say which inference method I'm using, right? So I'm using a one sample Z interval for P if conditions are met. And I need to go through and I need to check those conditions. So when I cannot spell a 3-letter word. So when I'm checking those conditions, I'm looking at randomness. I cannot forget that one, even though it's not a calculation. Okay, so was it random? Well, it says here that it was a random sample. Okay, I'm looking at 10% conditions, right? So for that, I have 439 times 10 equals 4,390. Okay, so there are more than 4,390 U.S. teenagers aged 13 to 17, so 10% conditions are met. And then I'm looking at large counts, right? And for large counts, I'm looking at NP, right? My success, okay, versus my failure. Okay, so N times P here, my success is going to be 246 of them said yes. Okay, my failures would be 193. Both of those are greater than or equal to 10. So my large counts conditions are met. So I've done my statement in part 1. I've planned it out in part 2. Okay, and so my random conditions were met. And now I'm moving on to the do in part 3. So step 3 is my doing. Okay, so my p hat for this is 246 over 439, right, over my total sample size, okay, which is going to give me a p hat of 0.56. Okay, if I'm plugging this into my calculator, my inverse norm, in this case, my area, it asked me for 95% confidence, right? So when I draw my curve, right, I've got my probability here of 0.95, which only leaves me 0.5 left, only leaves me 0.05 left over. So when I split that in half for the two tails, I get a probability of 0.025 and a probability of 0.025. I can work backward from my table, or I can use my calculator with an inverse norm of an area of 0.025, a mean of 0, and a standard deviation of 1, which gives me negative 1.96, okay, which makes my critical value then, right, my critical value z equals 1.96. So now I need to show my other calculations. So let's clear some space here. So my rest of my calculations then to actually find my confidence interval, okay, I've got my statistic, which is 0.56, plus or minus my critical value, which is 1.96, times my standard error, right? So that my standard error is my p hat, so 0.56, my statistic minus 1, times 1 minus my statistic over my sample size, which is 439. Okay, and so that is 0.56 plus or minus 0.046, which gives me my final interval of 0.514 to 0.606. So that's all my work and calculations. Okay, and so step 4 is our conclusion. So our conclusion gives our statement again in context. So we are 95% confident, because that's what it asked me for, that the true proportion of U.S. teens aged 13 to 17 that believe sex should wait until marriage. So all of this is our context here, right? The U.S. teens aged 13 to 17 that believe sex should wait until marriage is captured by the interval 0.0514 to 0.606. Okay, or again, you can reword that slightly. We are 95% confident that the interval 0.514 to 0.606 captures the true proportion of U.S. teens aged 13 to 17 that believe sex should wait until marriage. You have to have all of that context. Okay, so the last thing that we can do is that we can calculate a sample, we can determine a sample size for a particular confidence interval for a population proportion with a particular margin of error, so a maximum margin of error. So when we do that, we solve this inequality here, and so we're looking for n, we're looking for the sample size. P hat, if in this case, is going to be a guessed value. I can guess that from previous experience or studies, so I can pull that from somewhere else. Or I can set that value to 0.5. When I set that value to 0.5, this is when my margin of error is going to be the largest. So I'm definitely going to be finding a sample size that is going to fit my margin, that's going to be less than or equal to my margin of error. So let's walk through an example of this. Okay, so in this example, I've got a company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that she will be required to pay for. One critical question is the degree of satisfaction with the company's customer service, measured on a 5-point scale. The president wants to estimate the proportion, P, of customers who are satisfied, that is, who chose either somewhat satisfied or very satisfied, the two highest levels on the 5-point scale. She decides that she wants the estimate to be within 3%, or basically a margin of error of 0.03, at a 95% confidence level. So how big of a sample will she need? Basically, she wants to know how much this is going to cost her to figure this information out, to figure out the satisfaction of her customers. So if I'm looking to do this here, so our formula for this, right, we've got our critical value of z times our p hat 1 minus p hat over n, right? We're trying to figure out what n is less than or equal to our margin of error. So if I'm looking for 95% confidence, right, so we've already done this a couple of times, right? My little tails that are left over is 0.025 and 0.025. So plugging that into your calculator, whether you have that memorized or not, on your AP test, you will need to show that work, either plugged into the calculator or using table A, right? But my critical value here is going to be 1.96, right? If I do my inverse norm on my calculator. So when I plug this in, hold on, let me clear the space. There's plenty of room to work here. Okay, so you're going to have your critical value of 1.96 times, I'm going to go ahead and substitute in 0.5 for my p hat, because that's when my margin of error would be the largest. Okay, I don't want my margin of error to be any greater than 0.03, and I'm looking here for in my sample size. So my next step then would be to multiply both sides times the square root of n, and then divide both sides times the square root, divide both sides by 0.03. Divide both sides by 0.03. Holy cow. So then I end up with 196 over 0.03 times the square root of 0.5 times 1 minus 0.5 is less than or equal to the square root of n. So from there I'm going to go ahead and square everything. So I need to go ahead and square everything. And so that gives me 1.96 over 0.03 squared times 0.5 times 1 minus 0.5 is less than or equal to n. And when I solve this, I get 1067.111 is less than or equal to n. Normal rounding rules would tell us that we would round down, and we would say we need a sample size of 1067. Okay? However, normal rounding rules do not apply here. We need to be sure that we round up, and we get a sample size of 1068 respondents. We need to be sure that we round up to ensure that our margin of error is no more than 3%. If we round down, because we have those few decimal places there, we could end up having a margin of error greater than 3%. Okay, so we'll do more of this work in class.